Hi, so we're going to do inverse of a 3 by 3 matrix. Okay, right, first of all, it's really important. Okay, you need to be able to find the inverse of a matrix. So you've seen the previous videos on inverse for 2 by 2 matrix, which is fairly straightforward, yeah, and it was useful, wasn't it, for being able to determine unknown matrices and the multiplication because there's no division, and also to solve simultaneous equations. Or similarly, with 3 dimensions, x, y, and z, okay, you need to find a 3 by 3 inverse as well. Now, despite the fact that you need to be able to do it, the method is just nuts. It's crazy. It's just, I hate it, to be honest. It's, you know, do I get up this morning and think, yes, I'm going to do 3 by 3 matrices inverses? No. When I go into a classroom about to teach inverse for 3 by 3 matrix, do I think this is going to be a great lesson? No. It's just because the method is just, it's just insane. You do it, you think, why? You know, it just works, okay? It just works. And to be honest, I've never really fully got into the details of why it works. Maybe someone will explain why it works. I don't think there's a need to know. It's just, you kind of need to know the method. And you'll see what I mean as I'm talking you through it. Okay. Now, somewhere in the upload folder, there's a Word document which has put a summary of this. I'm going over that exact same example. Okay. And there's a page of notes. I actually did quite well to condense it on 1 page of notes. Okay. It's quite a time-consuming thing. Should we crack on? Yeah, let's crack on. Let's get this over with. Okay, it needs to be known. Okay, but it is a time-consuming process. Okay, just hold on to the thought when I said, why? Why are we doing this? Okay, it's like, oh, this reminds me a lot of statistics work. It's like, why? You know, why do you even exist? Why do we have to worry about this? You know, yeah. Anyway, there you go. I've got. There, you can't see out of shot a list of instructions for me because I don't commit this to memory. You know, I've got other things I'd rather commit to memory, like standard integral results, things that are useful. Okay, sorry, this is useful. If you do matrices anyway. Right. So step 1, you need to find the determinant. Well, that's not news because we had to do that with the 2 by 2 matrix. Okay, how do you find the determinant of a 3 by 3 matrix? Okay, well, if matrix A is written like that, then in shorthand we can write det A, short for determinant, and then we put the modulus brackets. Now, have you done the vectors unit? And if so, do you remember doing this with the vector cross product? Okay, because there's a link there. Okay, the vector cross product method involves this. Do you remember the vector cross product? We have I, j, k there, and then the first vector there, and then the second vector there, like I, j, k, 1, 2, 3, 4, 5, 6 as an example. Do you remember that? It's exactly the same method. Okay. So if you've seen the vectors unit, brilliant. Okay. So determinant A is this. If you've not seen the vectors unit, okay, this is what you do. Okay. To find the determinant of this, okay, I'm going to put equals here because I need all that space right now. You first will take the first element, which is A. Okay. And then what you're going to do is you're going to multiply it by the determinant of this E, F, H, I. If you've seen the vectors unit, it's great. If you haven't seen the vectors unit, well, just in case, what you do is, let's get the EFH. You cross out every element in the same row and column as A. So can you see when I do that? I'm just left with EFHI. Okay, so you do A times EFHI. Okay, and then you move on to the next element there, which is B. You subtract that, okay, and you multiply by this determinant, D, F, G, I. Can you see what's happened there? You cross out every element in the same row and column. As that. Can you see you're left with D, F, G, I. Okay, and then you get into the last element, which is C, and you add C, and then you multiply by the determinant D, E, G, H. Okay, and so cross out every element in the same row and column as that. So D, E, G, H. All right, and that gives us our determinant. To work at each one of these, it's the same as a 2 by 2 determinant. You do EI subtract FH, DI subtract FG, DH subtract EG. Okay, you've got to remember the positive, negative, positive. Okay, and that gives us an answer. That gives us what the determinant actually is. Okay, it's already getting complicated, isn't it? For a 3 by 3 matrix. Imagine a 4 by 4 matrix. Find the determinant of that. Ooh, I'd like to have a guess as to what it is. Anyway, because this video is going to be long enough, let me just get straight into it. So hopefully you've got a note of that. That's the first step. You've got to find the determinant. Okay. Now, what we're going to do is we're going to find the inverse of a particular matrix, and let me write down what the matrix is going to be. Okay. So I'm going to call matrix A. So what is it? 1, 2, 4. Like that. It's the first row. -1, 3, 0. And then 0, 1, 5. Right. So what we're going to end up doing in this whole example is to find the inverse of that. So at the end we're going to write inverse of A is that. So the first thing we're going to do is work out the determinant. Do you remember why it's a good idea to work out the determinant first? While you're thinking about that, let's move on. Okay, keep that in the back of your mind, and I'll answer it after I've done this. So the determinant of this. Okay, well, if that's what matrix A is, then the determinant is going to be that, but with the modulus brackets. I'm not going to write it again just to save board space. Okay, but it's going to be 1. Let's put the 1 there, shall we? Multiplied by the determinant of 3015. There we go. And then subtract all that. Looks a bit like 15, doesn't it? You've got to be careful with matrices, okay? If you put the numbers too close together, when you look back in your notes, it could look like, that almost looked like a 15, didn't it? I know it's not, because it's got to have 4 elements, but, just try and keep the numbers spaced, right? And then subtract 2, and then it's going to be -1, 0, 0, 5. You see that? So if you just cross out those, you've got -1, 0, 0, 5. Just as with the 1, you've got 3, 0, 1, 5. And then added to 4, and then determinant of -1, 3, 0, 1. Okay, there we go, -1, 3, 0. Incidentally, if you have done the vectors, then you remember the races that we did. Did a few races, didn't we? Okay, if you haven't done the vectors, you probably think, oh, I'd like to do that. Okay, it's very late on because there's a lot of other vector stuff to get through first, but I think there's 3 races in total. Okay, yeah. So let's do this. So 3 times 5 is 15, subtract 0. So that's going to be 1 times 15, right? And then next, -1 times 5 is -5, and that's 0. So -5 times -2 is +10, right? And then here, -1 times 1, -1, 3 times, so -1 times 4 is -4. Okay, so 15 plus 10, subtract 4 is 21. Nice. I know it's right because I know the determinant is 21. Okay, I've been doing the same example for years, and I remember the determinant is 21, so that's good. So that's that. Okay, that's how to find the determinant. Okay, now remember that question I asked you? Why is it a good idea to find the determinant first? Well, just a reminder. Okay, what happens if the determinant is 0? What sort of matrix do we call it? Okay, it's called a singular matrix, isn't it? What's a singular matrix? It means it has no inverse. Because remember, what we're going to do at the end is, when we have our inverse matrix, we're going to write inverse of A is 1 over, and it's going to be 21, isn't it? And that's what our inverse is going to look like. Okay, remember we divide by the determinant first, and then we have the actual matrix. Okay, and that's all that is our inverse. Okay, and if the determinant is 0, obviously you can't divide by 0, undefined, and the matrix is called singular. So that's why I'm reminding you about why you should do this first. Step 1, find the determinant. Okay, just to see if it's singular or not. Okay, right. Moving on. Now, this is not going to be. Oh dear, what shall I do? Shall I leave that there? Yeah, I'm going to leave that there. Okay. I'll go on to step 2. Sorry, I know I stopped mid-conversation. Okay. Just because I want to come back to that. Okay, we'll come back to this. It's just going to be a little on the side, okay, for something that's coming up. Okay. At some point, we're going to have to find the transpose of a matrix. Okay, what is a transpose? Okay, well, first of all, you spell it like this: transpose. Okay, and the symbol for transpose is this A and then T, like that. Okay, kind of cool, because if you have AT followed by AT, it's like attacked. Those Imperial walkers in The Empire Strikes Back. Anyway, enough of that. So your AT, A transpose. What does transpose mean? Okay, I'm going to introduce it to you now, okay, just as an aside, because transpose is sometimes used when you're not finding the inverse as well. Okay. What it means is you transpose each row and write it as a column. So that if this is A, you do 1, 2, 4 as a column. So 1, 2, 4. And then the next row, -1, 3, 0, you write as a column, -1, 3, 0. And then here, 0, 1, 5, 0, 1, 5. So can you see? I've just written each of those 3 rows as columns, okay? If I transpose it again, what happens? I get back to A, don't I? Okay. So if I do A transpose, followed by another transpose, I go back to A. You can see that because I wrote that as columns. I'm just going to end up with that again. All right. So transposing just means rewrite the rows as columns. That's it. Okay. I could have introduced that later, but in the notes handout I gave you, I put transpose in there first. That's just a little thing. Okay. Right, moving on. Let's do step 2. Okay. Step 2 is to find the matrix of minors. Ooh, what is that? Matrix of minors. Okay. This is a very tedious little thing. Okay. So this is matrix A. Okay. We found the determinant. Great. We'll just keep that to one side. It's 21. We'll now work on this matrix again. What we need to do is we need to look at each element, and we need to replace each of these elements with what is called its minor. So replace 1 with its minor, 2 with its minor, 4 with its minor. Okay. So there's 9 of them to do. How do we do that? Okay. How do we do that? Okay. So I'm going to give you a few examples showing that. Okay. So let's take the first element. Yeah. Number 1. You just have to remember that I'm referring to that one there as opposed to that one there. The minor of 1. What we do is rather simple. Is a bit like finding the determinant. Okay. We cross out every element in the same row and column as that, and we're left with 3, 0, 1, 5, and we find the determinant of that. Okay? The determinant of 3, 0, 1, 5 is 15. Okay? Another example. Let's choose something else. Okay? Let's choose number 3 there, one right in the middle. Okay? Minor of 3. What we do is same again. We cross out every element in the same row and column as 3, so cross out all of those, and left with 1, 4, 0, 5. Okay, 1, 4, 0, 5, and we find the determinant of that, which is 1 times 5, subtract 0, so that's 5. Let's do one more, shall we? The minor of, which one should we go for? Number 1? Yeah? No, we've chosen. Number 5? Yeah, that'll do. Minor of 5. Can you see what we do? Same again, we cross out every element the same row and column, left with 1, 2, -1, 3, 1, 2, -1, 3, and work out the determinant of that. So it's 3, subtract -2, so it's 5. Yeah. Okay. So that's what we're doing. We've got to do that 9 times. Okay, you've got to do that 9 times. Okay, so those are just some simple examples. Okay. Right. So. I don't want to do this. No, I'm better rub this off. It's annoying I'm just a single board. Because it means I can't refer to this. I'll probably have to work out those again. Okay. So you've got matrix A as that. Okay. So what we call this the matrix of minors. Matrix of minors is, and we write it out as a matrix, you see. So let's just go. Right, what did I say that one was? 15? Yep, 15. Okay. Right, let's move on. Let's do that one. So it's going to be -5, subtract 0. Remember, all the zeros are really nice, aren't they? Makes our working much simpler, isn't it? And then 4, it's going to be -1. Yeah. And then move on to this one here. It's going to be 10, subtract 4, 6. And then this one here, I've already worked that out, haven't I? It's 5. And then this one here, it's going to be 1, And then this one here, it's negative 12. And this one here, no, I didn't work it out. It's 4. And then this one here, 3 plus 2 is 5. Okay, I'm going to check it. 15, negative 5, negative 1, 6, 5, 1, negative 12, 4, 5. Hooray. Done. So that's the matrix of mind. That's the first step. Okay. Already fairly time consuming that bit, wasn't it? Okay. So that's number 2. Find the matrix of minors. Okay. Right. Step 3. We need to find the matrix of cofactors. Ooh. What's the matrix of cofactors? Okay. Well, what we do is quite simple. Okay. What we're going to do is we're going to multiply. I'm going to use this term very loosely. Multiply by this plus, minus, plus, minus, plus, minus, plus, minus, plus. Okay. What I mean is we're going to multiply the corresponding element by a positive 1. That corresponding by a negative 1, that by a positive 1, negative 1, positive 1, negative 1, positive 1, negative 1, positive 1. Okay, that's what we're going to do. Now, to save some space, I'm just going to rewrite that with what I'm going to multiply it by. Okay, so if I just, so if I start there, so multiply it by positive 1, so it stays as 15. Multiply by negative 1, that becomes positive 5. Multiply by positive 1, stays as negative 1. You see that? This multiplied by negative 1, this multiplied by positive 1, this multiplied by negative 1, this multiplied by positive 1, multiplied by negative 1, multiplied by positive 1. See ya? And I'm just going to change that to what's called the matrix of cofactors. And I know exactly what question you're asking. It's the question that everyone wants to ask. Because it works. It's just one of the few things I just really don't like about maths sometimes, because maths should be like, there's a logical reason for doing this, we're doing this because of this, and if we do this, it works because of this. I can't give you a logical reason for this. It's like, it just is. And that doesn't sit well with me. It shouldn't sit well with anyone else either. But there you go, it's one of those things again. In case you're wondering, no, I'll say that to the end. I'll remember, don't worry. What have we got to do next? That was that was point 3, wasn't it? So point 3 was find the matrix of cofactors, which we have done. Point 4, I'll write down over here. You find the transpose of that matrix. Again. Why do somebody just decide to just swap the rows for the columns? Why? It's, you know, it's like a bunch of mathematicians have gone out to a pub. Yeah, a bar, whatever you call it, pub. My imagining is it's somewhere in England, or Scotland or Wales, or yeah, Britain, UK. And you know, they've had a few drinks, you know. And they're like, hey, let's come up with this method for finding the inverse of thing. Well, should we do this? Let's do this. And then after a few more drinks, say, no, let's just suddenly change everything. Replace the rows with the columns. Oh, at some point we should multiply by positive 1 or negative 1. Yeah, it seems like that, doesn't it? Some weird, random set of instructions that someone has written down. Okay, it's not like that, really. I'm sure someone spent a long, long time devising this method, but it kind of works. Yeah, I still don't like it. Find the transpose. Okay, so what we do is transpose that. Okay, so the transpose of this. Right, so rewrite every row as a column. So 15, 5, negative 1, 15, 5, negative 1, negative 6, 5, negative 1, negative 12. Ooh, squeeze that on. Negative 4, 5. Just check that. 15, 5, negative 1, negative 6, 5, negative 1, negative 12, negative 4, 5. Okay, find the transpose. Okay, that's that. And divide by the determinant. Okay. Step 5 is divide by the determinant, but you may as well do it in 2 goes. Okay. So it's that. I'm going to check my answer there. Okay, just check I've got it correct. Yep, seems to be fine. Okay, and that is it. That's our inverse. That is the inverse of matrix A. It is done. Okay. How are we going to check that works? Of course we're going to check it works. Okay. Because for the moment you've just seen a random selection of stuff that's been applied to this matrix and we come out with that. You want to have some sort of demonstration. Okay, it's rather important, given the whole method I've gone through, it's rather important you have a demonstration as to why that works. Okay, so let's just do this. So it doesn't matter which order we do it in. Okay, so A times A inverse. I'm going to put the 1 over 21 there. We can shift it's a constant scale of A. We can shift the 1 over 21 to wherever we want. Okay, and we're going to do 15, 5, negative 1, negative 6, 5, negative 1, negative 12, negative 4, 5, and of course we know what answer we're expecting, don't we? Okay, just make sure I've written it down properly, otherwise I won't get the required answer. We know what answer we're expecting, don't we? Yeah. We're expecting our density matrix, aren't we? So as long as we get 21, 21, 21, 0, zeros everywhere else, we can then divide by 21 and we're done. Okay, so 1 over 21, and then 15, it's 25, 21, yes. And then negative 6, that's 10, it's 4, subtract 4, 0, that's good. And then negative 12, negative 20 plus 20, all good so far. How are you doing with matrix multiplication, by the way? You at this standard now where you can just multiply them like that without drawing the things? Okay. Negative 15 plus 15, 0. Great. 6 plus 15, 21, 0. Yeah, 6 plus 15 plus 0, 21. 12, subtract 12 plus 0. That's great, looking good, isn't it? So 5, subtract 5, great. 0, 5, subtract 5, wonderful. And negative 4 plus 25, 21, hooray. In contrast to doing the inverse, matrix multiplication is looking pretty nice now, isn't it? At the first you probably thought, why are we doing this method of matrix multiplication? You're probably thinking, oh, that's pretty simple, I don't mind that now, after seeing how to do the inverse. Yeah, so that's it. Obviously it doesn't matter which order you do it in. If you have got the inclination to do so, just swap those around and check. You also get the identity matrix. Okay, that's a nice demonstration as to why that method works. Okay, I'll tell you what someone probably did. Someone probably had a matrix with A, B, C, D, E, F, G, H, I, and probably just found a way through lots of research of coming up with this method and just put it into some simple steps. Okay, you know, before the quadratic formula was introduced, you know, the one negative b plus minus root b squared minus 4 is all over 2a. That is something that's useful to commit to memory. This is not. Quadratic formula is useful to commit to memory. Okay, but before that was introduced, it was a set of instructions. Okay, so 1,000 years ago, you know, well before René Descartes, who came up with the quadratic formula, 1,000 years ago, it was a set of instructions. Okay, you got a quadratic. First step, do this. Second step, do this. Third step, do this. And it may just be that mathematicians of that time were having the same sort of conversation as I am now about why are we doing this, why does this work, and someone's like, well, no, it just works, just do it, you know, follow the instructions. And then Descartes came up with a nice handy formula. Okay, does that mean there's a nice handy please, someone come up with a better method, please, because this is just, you know, there is a slightly better method. Okay, I've got no idea why it's not taught in schools anymore. It's a method that I was taught, thank goodness, when I was at school. Otherwise, I'd never have heard of it. Okay, I'll show you in a separate video though, okay? But there's a nice, and the method for doing it is really nice, it's logical, there's a reason for doing it, it makes so much sense. It's like, oh, at last, great, I can do this again. Except this is the preferred method. And I don't know what it's going to be like at university, but it could just be that they require you to use this method here, which would be a shame. There you go. But I'll mention what other method actually is at some point. Okay. Before we go, you got time for something else? Because it kind of slipped my mind a little bit. As I was talking about transpose, you don't really need to know this, but it's just, I was going to do it at the time, but I completely forgot. As I was talking about transpose, I could have introduced this to you. What's called a symmetric matrix. Comes from the word symmetrical, of course. Okay. A symmetric matrix is such that a A transpose is equal to A. In other words, when you transpose, it makes no difference. Let me just show you an example of that. Okay. So 1, 2, 3. If I write that as the column, 1, 2, 3. Can you see? If I transpose that row, it's the same as the column. Okay. I'm going to do the same with this. Okay. 2, 5, 7. So 2, 5, 7, 2, 5, 7. Okay. And I'm just going to pick a number to go there. Let's just go 4. So can you see when I transpose that? Okay. The 1, 2, 3. I'm going to write it as a column. 1, 2, 3. And then 2, 5, 7. I'm going to write it as a column. 2, 5, 7. And then 3, 7, 4. 3, 7, 4. Can you see? I've got exactly the same. Okay. That's what's called a symmetric matrix. Okay. Why is that useful? Well, maybe at some point you'll find out why, but the stuff I'm doing, it's not really that useful, but I thought I'd just mention what a symmetric matrix is, okay? Because at least that's understandable, okay? At least you can understand that, okay? Right, a fairly long video, okay? But now you need to know how to find the inverse.